Hello everyone and welcome to another VASaviation video. In this VASaviation lesson we're going to go over the VFR navigation and we'll prepare a full routing and planning together using the main instruments and charts. This flight will be departing from Asturias Airport west to A Coruña, resimulating the exact route we followed in a previous flight. Make sure to check the channel to watch that video. We'll be departing west, follow the shoreline via the points Whiskey 1, Whiskey 2, and then geographical places such as Fall Village, Estaca de Bares Cape, Cabo Ortegal Cape, down to Whiskey 1 and destination. In the first column, we will write down our checkpoints. This may be airport visual reference points, villages, lakes, mountain peaks, or anything useful for our navigation and visual reference. It is recommended that the distance between these points is no longer than 30-40 nautical miles. The longer the lag, the greater the possible error. The second column is to assist the pilots with any navigational aid, such as VOR or NDB stations. In this case, I will support myself with the Victor Echo Sierra VOR and the Charlie Oscar Alpha NDB and their respective frequencies. Though we are flying VFR, such stations can be really useful to find ourselves or just endorse our navigation. It's now time to start planning our route of flight. The next column is about the course, which is the straight line between 2 points as measured over a map. To calculate the courses of our flight, we use the plotter instrument. This ruler helps us determine the distance in both statute or nautical miles, but also the true course. This instrument acts like a ruler, so we place it to measure the distance between our 2 points. Then we rotate the circular piece in order to align those arrows parallel to the meridian lines on the map and facing to the north. Now we can read our true course in one of the perpendicular arrows depending on the direction we're flying. The last part of our flight has a little complication if we want to fly direct from Cabo Ortegal to Whiskey 1, and that is that we have a restricted airspace in our way. Due to this area, we'll need to proceed via coastline to avoid, so we'll take a middle point, which can be a lighthouse. Be advised, I made a little big mistake when recording the video, treating this lighthouse as if it were Whiskey 1. Therefore, the final distance, then time, then fuel consumption will not be correct at the end of the routing. We should add 15 more miles to the flight itself, which is the distance between the lighthouse and Whiskey 1. That being said, we can use the notes to write these details down so that we are aware of this restriction at all times. Penetrating a restricted airspace without permission may result in serious troubles. We finish our track with the Whiskey 1 destination leg. Note I'm starting the leg from Whiskey 1 and not the lighthouse. That's where my mistake is. The leg lighthouse Whiskey 1 is missing. Our true course is duplicated on this navigation log format I'm using, so I just copy the data I've determined with the plotter into the TC column, which of course stands for true course. The next column is about the altitude. We could be very precise with the crossing altitudes at every single checkpoint, but that wouldn't make much of a difference. I personally like to point the climbs and descents just with arrows to know what the aircraft altitude is. Following the famous semicircular rule, we should be using even altitudes, so we decide to cruise at 4,500 feet. It's now time to have some knowledge about the wind we're going to encounter along the route, which will also directly affect our aircraft and flight in terms of heading and speed. A very great website that I use is called windy.com, which shows everything. We can visualize winds, clouds, base of clouds, temperature, precipitation, and not only that, but also at different altitudes. In our flight today, we'll take a look at the map of 850 hectopascals, which is 5,000 feet. This web is as simple as clicking wherever you want to, and it gives you the information you need. We'll be checking for wind components and temperature to fill in our navigation table. The next column tells us about the calibrated airspeed and the true airspeed. The calibrated airspeed is the indicated airspeed corrected for instrument and position error. For our application in low altitudes and low airspeed, we'll take the CAS as if it were our actual indicated airspeed. The difference would be insignificant in such low speeds. For my aircraft, nothing faster than 90 knots. We now take our CR3 instrument, or any similar you have, and calculate our true airspeed. We have to match our pressure altitude with the calibrator airspeed and then see what the task window shows, applying the temperature we previously discovered. We find our temperature and follow the line down to the task indication. Again, flying this low and this slow makes almost no difference between calibrated, indicated, and true airspeeds. We then consider our task equal to our ES, but I show you the process to determine true airspeed using CR3 instrument. I will finally fill in 90 knots along the flight, except for climbs and descents where I apply a plus minus 5 knots as a rule of thumb. Okay, let's determine how the wind is going to affect our flight. For this, the ZR3 will again help us a lot by flipping it over and using the wind component phase. The first thing we must do is align the task arrow with the numbers above. Be advised these numbers are represented in tenths, so 1-2 means 120 knots. We now rotate the inner disc and align our true course with the TC mark. Let's find our wind direction within the green circle and then the speed. Each of those inner green circles represent increments of 10 knots. The wind is blowing at 24 knots from 320, so we search for 320 and go 2 arcs and a half, departing from the center of the circle. From this point, we draw two straight lines to the perpendiculars. For crosswind component, we check the horizontal and we cross at 17 approximately. This means our crosswind component is 17 knots, but we indeed want to know the angle of drift this wind is causing our aircraft to compensate it. We find 17 on the outer scale and see the angle below, 11 degrees of drift to be compensated into the direction of wind. This actually is our true heading. The wind will also affect our speed, so we check for headwind or tailwind. We find 320 degrees, go down to 24 knots, that is 2 arcs and a half, and now draw a straight line into the vertical perpendicular. The result is in knots of tailwind or headwind, which we will add or subtract to our true airspeed in order to determine our ground speed. If we have a tailwind component, the wind will push the aircraft forward, therefore we will go faster. If we have a headwind component, the wind will push from ahead, therefore our ground speed would decrease. Magnetic forces affect navigation very much. If you haven't watched the video about compass behaviors and magnetic instruments, I highly recommend going and watch it, since it will help you understand the magnetic variation we're about to take into account here. Variation is known as the angle between the magnetic north and true north. Variation lines, also known as isogonic lines, are represented in maps with dashed lines and a number of degrees, west or east. If we are west, we will add the number of degrees to our true heading, as it is our case. If we are east, we will subtract the number of degrees to our true heading. Most of Spain is over the 2 west isogonic line, but west-northwest of the peninsula has a change to 3 west, so we'll take both corrections for our flight today. The compass heading is also affected by the behavior of the compass itself. The compass can malfunction or work improperly due to magnetic, friction or G-forces, other elements or instruments of the aircraft, the building and structure of the compass, etc. All these errors are known as deviation and are usually represented just below the compass on what is called the compass correction card. Compass deviation rarely exceeds 3 or 4 degrees, so we'll take compass heading equal to magnetic heading. Our legs are not longer than 30 miles, so that error would be negligible. We will now calculate the total distance of our flight by just adding all the partial distances that we previously measured with the plotter instrument. Then we subtract the total distance with each partial distance to calculate the remaining distance to destination on each point of the route. It's time for the times. The ETE box means estimated time en route. This is how long in time we estimate a particular leg to be. Calculating this is super simple by just using the rule of 3. Our ground speed is 73 knots. This means we fly 73 nautical miles within 1 hour or 60 minutes. How long will it take, at the same speed, to fly 14 nautical miles? Multiplication, division, and we're good to go. The box underneath is the actual time and route, and will be filled in once we're flying. Adding all these minutes will result on the total time of flight. Next column of time is the estimated time of arrival to a checkpoint. Let's say we depart at 10:30 in the morning and we want to know at what time we expect to arrive at each point. This is as simple as using the ETE we have just calculated before. Departing 10:30 plus 12 minutes of flight to the first checkpoint gives us an ETA of 10:42. We're supposed to be over Whiskey 1 at 10:42, plus 14 minutes of flight to Whiskey 2 gives us an ETA to Whiskey 2 of 10:56. The box underneath is the actual time of arrival and will be filled in once we're flying, when we'll see if we're going on time, ahead of time, or delayed. We'll now calculate the fuel consumption for this flight. Be advised these numbers are applied to my type of aircraft, so make sure to check your aircraft manual or pilot's operating handbook. We'll be better working in liters in this case. We use a standard of 45 liters per hour in climbs, 40 when cruising, and 35 when descending. Calculating the consumption for each leg is as simple as a rule of 3 again. We know a consumption of 45 liters per 60 minutes, so how many liters will the aircraft drink per the ETE of each leg? Make sure to use the proper consumption standard applied to each phase of your flight. The adding of all the partial consumptions will result on the total consumption. Another video about fuel planning will be coming soon to plan the correct fuel for taxi, trip, contingency, reserve, and alternate. Be advised this fuel is the estimated necessary fuel only for the trip. Total consumption subtracted by partial consumptions will result on a remaining fuel on board over a checkpoint. The right side of the table is for airport and weather significant or helpful information. Be advised I'm just improvising all this data as an example. Local weather information should be obtained to fill all these blanks in. ATC radio frequencies can also be filled in with useful frequencies that we may contact along the flight. Air traffic controllers are to help us, so having them on the line at all times could definitely save our necks in every situation. Field elevation information can be found on the map or the local airport charts and diagrams. All the information that we can collect is welcome. We finished the lesson about the VFR flight planning and routing. Many formats can be found on the internet, but them all follow the same standards. I really hope you enjoyed the content and learned new things about the aviation world. If you have also any questions related to this lesson or any other topic, don't hesitate and leave it right below on the comment section. It's VASaviation, frequency change approved, and see you guys.